Again, before I start, I'd like to thank Sustainable Buildings Canada for having me here. This is a really great event, and I'm excited to be here with everyone. There are a lot of familiar faces, and I'm excited to share some of our project work and also some of our thinking around reimagining the facade as something other than just a kit of parts that gets bolted onto a building and forgotten about, something that is dynamic and integrated and a key component in delivering low energy and high performance buildings. I want to start by doing a little bit of a philosophical exploration to try to lift us up to a maybe slightly higher level. You might be thinking, why do we have Greek words on the screen at the beginning of a facade engineering talk? Maybe Taki can fill us in, but I'm going to read this quote about these two words, and I was struck by this in trying to think about facades as something a little bit more exciting than glass and steel or concrete or whatever. Bios, to be sure, has a certain shadowy or symbolic resemblance to Zoe, but only the sort of resemblance there is between a photo and a place, or a statue and a person. A person who changes from having bios to having Zoe would have gone through as big a change as a statue which changed from being a carved stone to being a person, a real person. So I want us to think about Zoe in terms of the building as this grand life thing, not just a bunch of parts that we all individually design, that we integrate and see as a living, breathing, real entity that can benefit from all of our efforts. So let's think about the details, but also appreciate the big picture of Zoe. There you go, a little bit of philosophy for the morning. Okay, so let's, I'm going to set the stage a little bit. Some of these are familiar graphs and trends, so I won't spend too long on them. But first, to talk about health, GRESB introduced for the first time ever a health module in the assessment of existing buildings, which is an interesting milestone in the marketplace. And there has been an increase in people who are reporting on health and well-being content in their buildings. And so this is definitely an increasing trend. There will be more and more reporting on that. Currently, only 33% of buildings are reporting in the health module as part of GRESB, but that is increasing. So that is an encouraging trend. We know this statistic. I'm sure there are other equivalents which may slightly vary. 50% of the buildings that will be here in 2015 are currently here. So we have a retrofit imperative. Projects like Drew's, projects like Vivian's, Reimagine, and some of the projects that we'll see on the walking tour are included here. And those buildings have available energy savings of between 20 and 40%, depending on mechanical systems or enclosure retrofits, and I'm going to talk about some of the buildings and some of the savings that we've seen. We know this quite well from the Toronto Future Looking Weather and Climate Driver Study. It's getting bad. It's getting worse. We don't need to be reminded of it regularly, but it is important to keep it in the back of your mind that there's a reason we're doing this. We need to adapt. We need to have buildings that are more responsive to a changing climate. And in fact, the climate has changed. It's not changing, it is changing, but it has changed. And this is from our friends at RWDI, a study that they published looking at weather sets from the previous 30 years and then looking all the way out to 2040. And you can see this is in Toronto. Climate Zone 6 on the left-hand side has traditionally been our zone for heating and cooling. Interestingly, what I find in this graph with that blue line, if you look at historical data from 1992 to about 2013, that trend is certainly into Zone 5, but it's also extremely erratic compared to the previous data set. So year over year variability is increasing, and so that is demanding more and more of buildings and their ability to adapt and respond. So certainly our building enclosure designs should take that into account, that we have more variability and we have a definite warming trend. And then if you cast out into 2040, Toronto will likely be solidly in Zone 4, which is, to the earlier point about energy discussion, certainly more cooling driven than we are today. And so while we may spend a lot of time harping on thermal efficiency, we have to be mindful that we're actually facing a cooling reality more so than a heating reality. We can't forget the lessons we've learned with controlling thermal energy, but let's keep in mind where we're going. The City of Toronto has changed a lot over the years. The obelisk of the TD Centre was delivered to the city in the 60s. And since then, the built form has transformed in downtown, and we are faced with a much more intense urban environment, and our buildings need to respond to that environment, either from changing wind patterns or changing solar exposures, increased intensification. If people are closer to the wall, it's more important that that wall be comfortable to be beside. So if it's a poor thermal performer, and you're cramming more and more people into a space, those people are going to be grumpy. And those people pay the bills. Maybe, well, their bosses may pay the bills, but you get the point. So we must design our buildings to allow for this intensification and in response to the fact that we have aging assets, and there is something we need to do about it. So I'm going to breeze through 3 case studies and just give you a very general sense of the kinds of opportunities that exist in existing buildings, whether it's a full overclad, full renewal, or sort of bolting on extra parts. And as I mentioned, a couple of these are on the walking tour. If you haven't caught the hint, I'm really encouraging you to come on the walking tour. I think it'll be fun. This is 120 and 130 Adelaide Street. It'll be stop number 4. These are 2 aging buildings from the mid-60s and late 70s. We had done fairly extensive cladding investigations, IGU surveys and testing to sort of predict expected failure. And it became apparent that the owner would be facing 100% IGU glass replacement within the next maybe 10 years. So maybe less. So that's certainly within the planning horizon of a very large retrofit project. You can't just one day say, I'm going to replace all my glass and just do it on a 35-story tower. That requires planning. So once you get into that reality, your opportunities open up a lot more. And I'm sure that's Vivian's experience as well, that these projects take time, they take effort, and it takes a big team to do that. You can't just deliver that in a rapid way. And as I mentioned before, if you are already replacing all the glass, but you're not fixing the frame, you're missing an efficiency opportunity. If you're replacing the glass, you have a sunk cost. So you have to realize that, okay, I'm already spending millions of dollars on replacing all my glass. If I spent 10, 20, 30% more, that's when I would see some huge improvements. And that's what we're certainly seeing in this case. So this project is underway. We can't go on the site, but we'll go around the site. It's about half done on the tall tower, and the shorter tower's just getting started. But it is completely replacing and reimagining the appearance of the building. And in the end, we're seeing thermal performance improvements of between 30 and 60% for the vision or the opaque portion, which is a tremendous improvement of an existing office building. And so to put it into perspective, a reasonable double glazed new commercial office curtain wall would be around 1.9, which is what the retrofit is for 130 Adelaide. 120 is a different situation. The U value for that vision is 2.6. The design of the frame made improvements a little bit more challenging, but still we're seeing a 30% improvement, and we're getting a significant improvement on the spandrel. And then we're also helping with solar heat gain. So again, looking forward to the climate reality of longer heat waves, hotter overall temperatures, likely more solar exposure, more people in the building, an aging HVAC system that may struggle with those demands. We can use the facade to respond to that. The next building is also on the tour 401 Bay Street. This is I think, a 1960s office building. It has, similar to Vivian's example, a precast cladding system with strip windows. There were some issues with the precast. It has an aged appearance. Depending on which blogs you read, people may like that aged appearance, some people may not. But generally, single glazed windows, poor thermal performance, a great candidate for some kind of building renewal. In this case, we designed a 100% overclad solution. So applying a new curtain wall system on the exterior, insulating all of the precast panels on the exterior, improving air sealing, getting rid of the original single glazed windows, and then seeing the new glazed curtain wall in front of it. There's also a stabilization exercise happening here. So all of the precast that's on the outside is being reinforced and restrained onto the building. So the deterioration of the precast now is no longer an issue, and we're protecting it with new cladding. So future deterioration is not going to happen. And all told, this building is seeing a 72% improvement in window U value. So this is, again, similar or slightly better than a new commercial office building for Vision Glass. And the spandrel panel, the precast had a little bit of insulation in it, but we're still seeing a 50% improvement because we're adding a significant amount of insulation on the outboard side. And the estimated energy savings for this particular building as a result of this, just the cladding retrofit, was $750,000 a year. So I'm not saying that those energy savings will pay for this project, because this is an extraordinarily expensive project. These are all expensive projects, and you will not find an energy payback for a full cladding retrofit. But it doesn't hurt the pocketbook to save $750,000 a year. And if you have to do a significant amount of work anyways, then seeing these kinds of improvements by choosing a slightly different path is a huge benefit. So if you're going to fix your building anyways, reimagining it opens up a whole bunch of new opportunities. The last building I'm going to talk about is the OAA Headquarters. Work is currently ongoing. This was a really wonderful collaborative exercise over a number of years. We did early air tightness testing on the building, and the building was extraordinarily airtight. There were a number of other retrofits that had happened on the building, but this was an opportunity to do a whole building renewal, including HVAC, including the walls, including the windows, and that wonderful superstructure that hangs on the roof. Speaking about whoever it was talking about roofing, my understanding is that superstructure was originally designed to have solar panels on it. But when the building was built, the funding wasn't there, or the solar was too expensive. But today, it's a different reality, right? Solar is much more affordable, and this is going for carbon neutral as a net zero retrofit. And so now we're implementing solar panels on that superstructure, which was designed for it in the first place. So again, reimagining that, or I guess realizing the imagination at the time and executing on that is kind of an exciting opportunity. So here's just a few photos of in-process work. In the bottom right corner is a dynamic glass installation, so that's View's product. So it's solar responsive. It's changing its tint based on the solar exposure and helping control solar heat gain. And we're doing other wall and soffit repairs or upgrades. The other thing that we have to keep in mind is this was already a very airtight building, and airtightness is a huge energy consumer. So all of this work, as we tear out windows and we destroy soffits, we have to make sure that when we build those things back again, that we meet that high level of airtightness that we were expecting, that we had before. So there will be some follow-up testing just to validate that we're still seeing that airtightness. And as I mentioned, this is a carbon neutral, net zero energy target. There's a whole bunch of stuff going on here that I'm not talking about. I'm talking about cladding, because that's what I like to talk about. There's a whole bunch of energy stuff going on here. But I would say that a lot of the energy stuff, and I'll talk about that in the next few slides, are enabled by good enclosures. And if I'm going to talk about it, I better get moving. So let's look a little bit into the future. I'm calling this future-looking facade design. What kind of things are we seeing on the horizon? How can we integrate some of these technologies today into our business? And how do we design good enclosures that enable good design or good HVAC? Not to belabor the point, but this is all underpinned by quality. If we build poorly, but it's awesome stuff, it's not going to matter, right? If you build garbage, you get garbage, even if you use gold. So I can build, a gold fascia on my building, but if I use the wrong fasteners, it's going to fall off, and I got to replace it. So, maybe it's because I read the Other Motorcycle Maintenance or something. I'm really on this quality kick. We have a responsibility to build well, and that is a huge component of health. If we don't build well, we affect health. I'll leave it at that. These next two slides speak a little bit about the types of HVAC systems that deliver energy to space. So I'm all about controlling loads, right? If I do a good enclosure, then I reduce the loads on the building. How that energy is delivered to the space is the mechanical designer's realm. If the enclosure is good enough, then that enables low energy, high performance systems. It's maybe a little bit hard to read this, but if you look over at the far right, if I have a high performance target of an R18 wall and 40% window to wall ratio with a U value of 0.16, again, this is imperial, so sorry for the switch, that's a whole wall R value of windows and walls together of R10. Well, within that zone, now if you look on the left-hand side, I can use in-floor radiant heat for both the corner or the side office. I can use VRF. But if I go over to the next right vertical line, if I just follow SB10, the old SB10, if I'm above the limit of radiant in-floor heating. So my enclosure is not good enough to keep the space comfortable if I use in-floor heating. So I can't deliver I can't deliver energy in a low-use way with a poor enclosure. Same is true with cooling. We have various limits of chilled beam BTU output. Chilled beams badly designed as well can give you a little bit more BTU output, but might not necessarily be the best choice. And then radiant cooling, like in slab, for example. So again, depending on your enclosure selection, that enables good low energy design. We cannot take thermal performance for granted. We know that attaching cladding significantly undermines the performance of the insulation that we've just spent to put on the outside of the building by as much as 50%. So don't get your hopes up if you put 6 inches of insulation there and then you install continuous Z-girts. You're really undermining yourself. So we have other creative ways of using clips or other design systems to separate the cladding from the structure and get better ROI for your insulation. So the finance people perk up, ROI, yeah, I like that. I want to get my value out of my insulation. Well, that means you might have to invest in slightly different cladding attachment systems. So I'm starting off sort of basic, I understand, but quality, good thermal performance, make sure you get what you pay for. People have probably heard of this technology. This is from Italy. Smog-Eating sounds way better than like photocatalytic. So I put Smog-Eating because that sounds really cool. The stats that they have, if this were deployed on 15% of buildings in Milan, because this is an Italian company that came out with this, it would reduce air pollution in the area by 50%. It's only effective up to a certain height, and the rainwater washes the activated or the collected smog off during a rain event. Fortunately, it's a non-toxic wash that is basically a saline type solution. So it converts the smog into something that's non-toxic, and then it washes off the building, and then it does its job again, which is kind of a neat product. I'm going to highlight a few project examples. I'm going to go quickly because we have about 6 minutes. Just to show you a couple highly glazed buildings that have low energy performance, low energy use intensity, so really great energy performance. And I've bolded the things that are contributing to that from a cladding perspective. So this particular building has a double facade and it uses triple glazed windows. So these are, I'm sure this facade system is enabling a low energy system. That's not possible with a standard enclosure. This is also passive house certified. It's in Austria. And the EUI is 11.1, which is great compared to, I think, the BOMA standard of 27. Everyone is very familiar with Manitoba Hydro. Again, an EUI of 7.9. This has this giant atrium that helps enable ventilation. There are operable windows in that space. it has some exposed mass for thermal blunting of that effect of heat gain. But again, the facade is certainly enabling that. There is a double skin facade on this south atrium to help improve the performance of that building too. This building's in Pittsburgh. I love this series of images. You see the person in the middle center at the bottom. They're walking around this circulation space that's on the exterior of the building that is part of the double skin facade. So it's an integrated HVAC delivery system that also happens to be part of the cladding and circulation space. There was a fairly large mock-up done to test functionality and make sure that this would actually work, because this is quite a unique approach to cladding and HVAC integration. Energy use intensity of 8.6, and there are operable windows. All the louvers are automated, so climate responsive design is becoming more normal and is entering into buildings more commonly than we would expect or have been in the past doing so. And yeah, so this is a 3-foot wide, they call it the porch, which, I mean, I'm a porch guy. On my street, every once in a while, someone closes in a porch, and it's like a little wrench on my heart, right? It's like, oh, you know, I'm a porch guy. I want people sitting on their porch and saying hi to each other. So I like that they call it a porch. I'm not sure how many times they say hi to people walking through there, but I still like the idea, this notion of the facade with a porch, which is one of the reasons I picked this. In Toronto, our commercial office building experience would suggest that the trend is towards triple glazing and 100% glazing. And the reason for that is spandrel panels, so the opaque portion of the wall. People who attend the SBC Charrettes know my passion for railing against spandrel panels. They have very poor thermal performance. So if you're going to have an 80% glazed building, and you're going to use double glazed, or even if you're going to use triple glazed, let's go triple glazed, and then you have 20% spandrel, that spandrel is going to give you about an R3, maybe 2.5, depending on how big it is. Because once it's really small, all the heat just goes through the aluminum. It doesn't know to stop at the insulation. It wants to go out through the aluminum. So your effective thermal performance is very low because your spandrel is performing worse than your glass. So when you think about it, if you went 100% glass but used triple glazing, your effective wall R value is probably 9-ish. So that's actually really good for a tall commercial office building. And that's the trend in some of the more recent buildings that are being designed. And then I threw in a photo in the bottom left of, this is St. James Cathedral, one of their administration buildings in the back. Again, 100% glazed with some kind of glazed fins to sort of, as an architectural feature, but also as a bit of a shading device. In addition to 100% glazing, we can look at things like dynamically responsive glass. And so in the bottom right, this is not view glass, this is another photochromic glass. And you can sort of make out the slightly lighter line right next to the mullion, which is a response of a piece of structure that is shading that part of the glass, or was about a half an hour before I took this picture. And so it hasn't quite turned to its tint yet. So you can see how it's responding photodynamically to the influx of light, or to the solar exposure. And the last thing I'm going to talk about in closing, I have a minute left. This is a project that our built ecology team in the US worked on with HOK. They call it the Circadian curtain wall. It's a sort of a bulbous curtain wall design, has integrated shading, some integrated HVAC. It also is solar and dynamically responsive depending on the exposure and the solar radiation coming into the space. It really is that highly glazed type commercial office that you expect or has been the norm. And they call it the Circadian curtain wall because they're saying it sort of draws on that natural connection between people and daylight and darkness, and it enhances that by controlling the climate as a result of that highly glazed enclosure. So we want to be connected to nature. We want to see outside. We know that people in hospitals heal more quickly when they have views of natural spaces. But that can come at an energy or a comfort penalty. And so this is a response to that, to help control high climate loads while still allowing this great connection to nature. So thank you very much for that. I think Larry's going to come up, maybe guide some questions, and I will be around. I might mention the walking tour if I haven't already done so. Thanks.